for B3, right, we're just use the same exact approach. So in this case right here, right, what we're trying to form is, magnesium oxide, in this case, right? So that starts off from solid magnesium and O2 gas in these cases. And so we just do the exact same approach, right? So we have to get everything into the gas phase. And so the magnesium, right, it's a solid. And so we have to include the sublimation to form magnesium, gas. We have to do the ionization, right? So we're going up to magnesium 2+. So we have to do the first ionization, right, of the magnesium. Oh, I actually have here the values, right? So we'll actually see what the ionization energy is for magnesium, right? And it's only just like double of what, the first one is. So we have that. So then, we form magnesium plus, but then what we want to do is we want to make sure that we then also form the 2+ in that case, right? So that's then the ionization energy for magnesium plus. And so then in the case of O2, right, we have to, break apart that bond. And so that's going to be then half of the bond energy in that case that we need to form O gaseous in this case, right? And so now, right, we're trying to go to O2 minus. And so by going to O2 minus, what we're going to be doing, right, is first having the first electron affinity for oxygen, right? And so that's going to be O minus gas then. And so then again, right, we have to do then the second one. So now this is going to be the electron affinity for O minus. And that's going to form O2 minus in the gas phase. And so both of those then come together, and that forms the lattice energy of magnesium oxide, right? And so that all will be equal to the delta H of formation of magnesium oxide. And so the question is, right, what is that value? And so the way that you approach that is same way that we did it for A3 for A3A, right? So we, if we write out what the whole equation is in this case, right? So delta HF formation of magnesium oxide is going to be equal to the delta H of sublimation of magnesium plus the ionization energy of magnesium plus the ionization energy of magnesium plus half of the bond energy of O2 plus the electron affinity of oxygen plus the electron affinity of O minus plus the lattice energy of magnesium oxide. Right? And so since we're trying to figure out what the lattice or the electron affinity is for O minus, all we have to do is just simply rearrange all of this. So what we get is that the electron affinity of O minus is equal to delta HF of magnesium oxide minus everything else that we had before, right? So minus delta H of sublimation of magnesium plus the ionization energy of magnesium plus the ionization energy of magnesium plus 1/2 bond energy of O2 plus the electron affinity of just simply oxygen plus the lattice energy of magnesium oxide. Right? So we have all of that. So now all we have to do is just plug in all of our values. So delta HF, right, is right, the delta H formation of magnesium oxide is negative 859 kilojoules per mole minus, right, the delta H of sublimation is 37 kilojoules per mole plus the ionization energy of magnesium, right? Again, both of those are given in electron volts. And so the way that we convert that, right, is that we can multiply that by the conversion amount of that. So that was, let me just look at the previous packet again, 1.60218 times 10 to the negative 19 joules, right? So that gives for 1 EV times 6.02 times 10 to the 23rd, right? Gives us the per mole. And then we convert that, then 1 kilojoule is 1,000 joules. So what we get then, we plug in our values for that. So we have for the ionization energy of magnesium, so 7.65 times 1.60218 times 10 to the negative 19 times 6.02 times 10 to the 23rd time, or divided by 1,000. Right, so that comes out to being 700 Oh no, fucking pen. So there we go. 738 kilojoules per mole, right? And then for the other one, we can do the same thing where we just plug it into that same equation. And so that's then 15.04. So that comes out to 1,451 kilojoules per mole, right? So I plug those values in. So 738 kilojoules per mole plus 1,451 kilojoules per mole plus 1/2 of 494 kilojoules per mole plus negative 141 kilojoules per mole plus negative 859 kilojoules per mole. Right, so we do all of that, and now we just need to plug in chug. So we have negative 859 minus negative 37 plus 738 plus 1451 plus half of 494 plus negative 141 plus negative 859 gives us negative 2,000. Something is off because I got negative 2,258. And I know that's not correct. It's supposed to be negative. It's supposed to be positive 743. So something somewhere. Wait a second. So, okay, so that's positive. I don't know why I put a negative there. Negative 859, 37, 738, 1451. Half of 494, negative 141, negative 859. Oh, I put in the wrong number at the end. Haha. That's one thing, very important thing. Right, so it's not negative 859. I wasn't paying attention. It's negative 3,934 kilojoules per mole. Right, so that's one important thing. Always double check, right, that you're using the right values when you're transferring it over. So let me just do this again, right? So we have negative 3,934 there at the end, and so that gives us 743. Negative or positive 743. Right, but that's yeah, right there, right. And so the important thing to think about, right, why people I think typically get tripped up on that question is because the electron affinity is positive, whereas you would think that you wouldn't have to put energy in to form O2 minus because you're forming a full octet around that oxygen to form that species, but there has to be something that balances it out, so to say. And that happens in the case, right, where the lattice energy is so high, right, it's close to 4,000 kilojoules per mole, right, balances out the amount of energy required both to ionize the magnesium twice, but also, right, to put more and more electrons onto that oxygen in those cases. And so that's where all of that comes from, right, is the stability that the lattice energy provides into forming those ions in those cases. But yeah, so I mean that's how you do B3, right? Very similar to A3, very similar approach.